Okay, lesson 12. We're going to talk about molecular compounds mostly, and this will be a little bit of review for you. So the first part's a review, but we're going to talk about molecular structures, and we already know that, I'm just going to actually chop this off here. Molecular compounds have covalent bonds. We talked about that kind of yesterday a little bit, of course, review. You had a quiz on it, and you drew some lines, hopefully, at some point, that exist between specific pairs of atoms. It is possible to predict the three-dimensional shape of many small molecules based on their Lewis structures, or electron dot diagrams, of course. So we've kind of already done this a little bit, and I've kind of set you up for this already, but we're going to look at some different shapes that these molecular compounds tend to form, all right? We've drawn them already, so now that's the hard part. Now that we've drawn them, we'll get a little more practice with that, but then we're going to kind of link them up to a specific shape that they go with. All right? Sound good? Everyone's good there? Yes? Moving on? All right. So we do have a few notes here before we get to the actual shapes, but not too bad. I think I've talked about this before, something called VSEPR. Yes? Does that sound familiar? VSEPR stands for valence shell electron pair repulsion theory. That sounds complicated, but we'll talk about that. Allows the prediction of three-dimensional shapes. And the theory is based on the electrostatic repulsion of electron pairs that causes them to take positions as far apart as possible. And I want to put on here as well, how far can I go down here? Repulsion is maximized. All right, so again, it sounds complicated, but basically we've talked about this before, where pairs of electrons will pair up, okay, whether it's a bond or that lone pair that we talked about at the top of an atom, and those pairs of electrons repel each other, and we've kind of drawn that before, right, where we try to get other atoms as far apart as possible from one another, and we try to spread things out, yes? And so the key here is that the repulsion has to be maximized. That's key, okay, so make sure you write that down as well. It's, yes, positions as far apart as possible because the repulsion is maximized, okay, between these pairs of electrons, all right? And we're going to kind of look at that, and I'm going to kind of prove that to you as we go here. Yeah, I think we will copy this. Basically, it says the following, okay? So just maybe wait for 1 second here before you start copying. I'll give you time. Basically what this said, I know this looks, what's LP? LP is a lone pair, okay? Lone pairs are those like two dots that are on top of the atom kind of thing by themselves, and they take up a position, yes? Okay, like nitrogen. You know how nitrogen looks like this, right? And then, of course, we have those there. These would be the bonding pairs probably, yes? Those are the bonding pairs. And then this is the lone pair here, yes? Okay, of the top part. So the lone pair here, okay, what they're saying is if you have lone pairs, they repel the most, okay? They push away from them the most. Lone pairs push away the most. Bonding pairs are the least, okay? So if you had, for example, a lone pair and a lone pair, that repels more, those push more than a lone pair and a bonding pair, and that pushes more, greater than, a bonding pair and a bonding pair. That's basically what that's saying. Basically, all you need to know is this. The more lone pairs you have, the more they push. You know, if you have one lone pair, it pushes a little bit. If you have all bonding pairs, they all kind of push the same. Okay, that's kind of what they're saying. All right, go ahead. If a molecule has more than one central atom, which we've run into this before. Remember, I don't know if you remember, but hydrogen peroxide, H2O2. If a molecule has more than one central atom, we need to kind of break it into sections, basically, because we can only name simple molecules. That's all we're doing here. And I've told you this before. We only have 6 basic shapes. And so at some point, we kind of got to break it down into sections if you want. So if a molecule has more than one central atom, it's probably best or advisable to separate them and predict separate shapes for each central atom. Okay, so if we had 2 central atoms, like for example with 2 carbons, and then 4 hydrogens, what would the shape around each carbon be? We'll take a look at that. I'm not too concerned about this. This will happen, but again, we're going to stick with the basic ones for the most part. So, I lied. I forgot about this. Yeah, we're going to have to copy this, I guess. We're going to use a general symbol, or sometimes I like to call it kind of a general formula to classify shapes. A is going to represent the central atom. X is the atoms that are bonded to the central atom. E represents number of lone pairs on the central atom. And the general formula usually you're going to see is AX, little m, En, and M is the number of atoms bonded to the central atom, and E is the number of lone pairs. That sounds really confusing. I'll let you copy that. It sounds confusing, but once you see the examples, it's going to be, it's not that bad at all. It sounds like a lot, but it's not. Our first one that you are gonna have to copy this, but the first one is called linear. Okay, linear has this symbol here, which is AX2. Okay, bond angle is 180 degrees. We're gonna have to know that as well. And this part's not super important. This part's not. However, you can still copy it. It usually has 2 double bonds or a single and a triple. And I'll give you some examples of this structure. Okay, I'll let you just copy that. Some examples of linear structures. I'm going to give you a couple of examples, but what we have to do is basically same thing we've done before. We have to be able to draw the molecule first. All right, then we can kind of match it up to this formula, AX2. We can say, oh, AX2, that's linear. It's got a bond angle of 180, and then we're going to add on to that down the road. All right, so, but the first thing is we have to be able to draw them. And of course, so we're kind of doing, I don't want to say we're doing this backwards, but we kind of a little bit are, because this is what linear looks like. And now I'm going to give you some examples, but this is kind of where you would start if I gave you these. So the first one we're going to talk about is carbon dioxide. Would be an example of a linear structure. All right, linear shape actually is what we call it. If I said, hey, we have some carbon dioxide, the first thing is we want to draw it. So I'd say, okay, well, we're gonna start with some neutral atoms like we did today on our little quiz there, hopefully. You know, there's carbon, right? Here's oxygen, and there's another oxygen. And you could count up electrons if you wanted to and do it that way. That's up to you. We've drawn this one before, haven't we? Yes, remember? Which one would I put in the middle? You'd say carbon. Good answer. Okay, carbon in the middle. If it's going to be in the middle, I'd put one O there probably. I'd kind of flip it over and put the other O here, right? Because if carbon's going to be my central atom, I want to have 2 things on either side, yes. I'd probably start connecting some dots here. There's a bond there, there's a bond there, yes. So connect the outside ones to the inside ones, okay? Next thing I'd do is probably say, okay, do I have an octet around each one? You'd say probably no, right? Because we have some unpaired electrons. So I'd say, oh, maybe let's take these 2 out here, for example, and let's put that there. Okay, and then let's maybe take this pair, and that pair, or sorry, that single one and that single one, and make a pair there. Yeah. Okay. Again, you know, we talked a little, now that we're starting to talk about VSEPR, we want to get those pairs of electrons repelling each other, right? So I would say that's probably not maybe the very best diagram, but I'd probably say something like this, where this bonding pair is away from that bonding pair. And then any pairs of electrons that we have are kind of further away from everything else. So that's why we'd probably put 2 there, 2 there, 2 there, and 2 there. We kind of try and want to get these pairs of electrons away from each other, yes? Right? Now, that's what you do first. And then we'll just finish this off today and we'll be done. So just be patient here. The next thing I need you to do is this, okay? We have to kind of put this into perspective with our formula or our general symbol. So we use A to represent any central atom. Well, this is my A, isn't it? Right? A is my central atom. We use an X to represent any atom. It doesn't matter what kind of atom. It could be different atoms. Doesn't matter. Any atom that's bonded to the central one, we call it X. So I'm just going to go double bond X, double bond X, okay? Even if it was a different atom, so if it was a different atom but had the same kind of look to it, I call it X. It doesn't matter, right? And then I use an E to represent any lone pairs on the central atom. So here's my central atom. Do you see any lone pairs there? So we're not going to write down the E. All right. This is called AXX or AX2, right? I got two atoms, whatever they are, and they're bonded to the central atom. Once I know that, I say, hey, AX2, I studied, so I know that this is linear. Linear has a bond angle of 180. Okay, and it looks like this. It looks like a linear. It looks like a line. This bond angle right there is 180. Okay, between bonds. Now it's going to sound stupid, but it has to be between bonds. Okay, we'll talk about that tomorrow. Okay, we'll stop there for today.